How can that?
I do, however, do the grilling in my house because gender roles. You know?
Gender norms.
Yes.
I just thought it was funny.
My wife's in the army and I'm at home in an apron.
All right. Let's do some lecture. This is our last lecture on how dynamic systems, or how measurement systems can be understood as dynamic systems. Okay. So chapter 3 has been all about that. 10 lectures. So this is our biggest chapter so far. It's taken us a couple weeks to get through it, but we've at least 2, maybe 3 weeks. 3 weeks to get through it, so it's been a challenge.
we did 3 lectures on Monday.
Oh yeah.
So
in any case, it's been some period of time. I would guess it's been 3 weeks. Maybe 2. In any case. What? Oh, let's not distract me anymore. Let's talk about phase linearity instead. So we've got in the last lecture we talked about how to find the output of a measurement system when the thing you're trying to measure, or the input to the measurement system, is periodic but not sinusoidal. Okay? And how do we approach that? Do you guys remember? So close, yeah. So Fourier series, right? So periodic, so we could do Fourier series of it, and then we learned how to take that. We figured out how to find the output. So we took the Fourier series of the input, and then how do we find the output from that? We were all, and then some math happens. Do you remember what we did? Well, first off, we just ignored transients, right? We were like, let's just talk about steady state response. And then we were like, hey, so if you put in a sinusoid and you care about the steady state sinusoidal response to that, then there's some notes. Then you can. So if you put in a sinusoid and you get out a sinusoid, the only thing that change are the only things that change are the magnitude and the phase, right? And they change by the magnitude multiplies the frequency response function magnitude, and the phase sums with the frequency response function phase. That's the only thing. That's the only way that a sine wave changes. So we were like, well, if you can write the input as a Fourier series, it's just a sum of a bunch of sinusoids. So we could do that for each sinusoid in the series, and then we could get our output Fourier series, or output spectrum. And we did that graphically. And then I was like, hey, we should have looked at this in the time domain. I included it in this one, actually. So you guys will be able to see it. I did send it on Slack. It was not nailing it. All right, so good. So let's talk about phase linearity, which is essentially just another aspect of not nailing it. Okay, so the source for this exercise is in the notebooks directory. We observed in the last lecture that significant distortion of a non-sinusoidal periodic function can occur. Due to the system's significant underdamping and confounded by the input spectral component right on the natural frequency, significant resonance distorted the signal. But for most measurement systems, we prefer damping ratios nearer unity. So we had a damping ratio of like 0.1 for that example. So there was a pretty significant resonance that was happening there, and so we typically don't like to live in that range. So the question is that if your damping ratio is near unity, can these systems also exhibit distortion? And the answer is yes. So I'm going to then try to expand on why that's true. So consider the Fourier series of a system with this periodic input. So this is just a Fourier series written down. So A0, n omega 1 is just another way of writing n, so 2 pi n divided by the period t, right? So that we wrote it in terms of the fundamental frequency instead, because we like to mix it up and be different. So we derived the output to this, remember, to be this. So all we did was we got out a sum of sinusoids that were at the same frequency and the same phase, except that we had these extra terms in here. We scaled the amplitudes by this magnitude of the frequency response function, and we summed the phase with the phase of the frequency response function. So that was what we did last time, and we thought we were pretty cool. I remember thinking that. I was like, yeah, we're pretty cool. So let the system's phase shift, angle h of j omega, depend linearly on omega. So this is not generally true, but I'm just going to say, let's consider this possibility. Let's say, let's let this happen. What's the result? In this case, the fundamental component has this much shift, right? So if you look at the fundamental component, that's when n equals 1. So if you looked at this, everywhere you see an n, you'd plug in a 1. So this term would just be angle h of j omega 1. So that's why I said it has shift angle h of j omega 1. The second component has shift 2 times h of j omega 1. And the reason for that is that we said it's linear. So if you have a linear system, if you double the input, you double the output. I mean, you could even just think of a linear function. Doesn't have to have any particular slope. Slope is actually, this is independent of slope, but if you have, this is your input, this length here, and then this was your output, the y. So if this was x1 and this was y1, if you doubled x1 and you went to x2, then you would get out y2. This is like a similar triangles analysis, right? So it's true of any slope here. And so then we could go to the third harmonic, and the phase shift would be 3 times the phase shift of the first harmonic, and on and on. So each subsequent component would be n of these fundamental phase shifts. So the nth sinusoid in the sum. So I'm just gonna pull this sine term out and inspect it, because it's kind of like, there's a lot going on in this equation. So I'll pull the sine out. I'm just going to look at it more closely. So assuming that we have this linear phase shift, we showed that each of the phase shifts can be expressed as n times the angle of h of j omega 1. So n times the fundamental phase shift. And then you can factor out n from these two terms. I switched the phi and the angle term so that I could factor out the n. And I end up with this expression here. Now we're going to do a little variable change. I'm going to say that theta, which is like the Greek version of t, right? So that's why we're using theta. Also, we're using trig stuff, and it just feels right. So we're going to use theta. So theta we're going to define as being t plus the fundamental phase shift divided by the fundamental frequency, angular frequency. Okay. If we use that, then we can rewrite 350 as sine n omega 1 theta plus phi n. So within a time shift, then, this is exactly the same as the input. So the input here was n omega 1 t. This is n omega 1 theta. So n omega 1 t plus phi. This is n omega 1 theta plus phi. So the output is just the input, but time shifted, right? Time shifted some amount, which depends on the phase. Depends on the phase of that fundamental. So that's what we want, right? We want our output. I mean, in measurement systems, this is not true of a lot of systems, but of measurement systems, what we're trying to do is we're trying to get the output to look like the input, because we're trying to get our measurement device to reflect what its input is, because we're trying to measure what its input is. So we're trying to get its output to look like its input. And we don't want to distort it. And so one way not to distort it is to have this linearly varying phase shift. And your resulting output signal is exactly the same as the input, just time shifted. Which time shifted is fine. Like, we can take that into account. I mean, it's not always fine, but in a lot of cases it's fine. As long as it doesn't distort the signal, it can be shifted a little bit. Therefore, for an input with dominant frequency components below some frequency omega c, if the magnitude ratio below omega c is approximately 1, so that's our first requirement. So that is violated by the case when the damping ratio is like 0.1, right? So you get that big resonance peak, and the magnitude ratio is not 1. So you want the system to have a damping ratio of around 1, so that the magnitude ratio stays about 1, up to some frequency omega c. And if the measurement system's phase shift below omega c is approximately linear in frequency, so that's what we just discovered, was that if it's linear in frequency for all of the dominant all the dominant components of the Fourier series of the input, then the output should have the same amplitude and shape as the input with a time lag. So that's ideal, right? It's an important result. Let omega c be the cutoff frequency, above which the magnitude ratio declines and phase shift becomes significant. So omega c for a system is something that, so the cutoff frequency is something that, for a measurement system, we're saying, okay, if you measure stuff that doesn't have any frequency components above this cutoff frequency, like the measurement system will reflect what the input signal looks like. But if you go above that, if you put in something that has higher frequency components than that, then you're going to get distortion. So that's an important thing to be aware of when you're going to measure a signal. Any periodic input with significant frequency components above omega c will exhibit distortion. Therefore, it is not simply the resonance that distorted the signal from the previous lecture. It's also this phase nonlinearity. So we explore this further in further detail by applying the square wave to the system with a single difference from the last lecture. Now the damping ratio is zeta equals 0.707. So I'm going to do graphs for both zeta equals 0.1 and zeta equals 0.707 and look at the difference. Okay. 0.707 might be a floating point number you're familiar with. It's the square root of 2 over 2, right? Or the square root of 1 over, or it's 1 over, yeah, 1 over square root of 2, or square root of 1/2. So it is, it's not obvious why that's a good number, but it's, if you are to look at the lowest damping for which you get no resonant peak that comes up in the second order response, then damping of 0.707 is that. So it's like as wide as possible, but it's also flat. It doesn't have that resonance in it. So it's nice. You can, I would say that it's like considered to be like the sort of like the golden damping ratio. Like this is the one that you want to use for a lot of measurement systems. It's not perfect, but it balances several things. If you go too high on damping ratio, what ends up happening is your system responds really slowly. And that's not very good for a measurement system. If you go too low on damping ratio, you get these resonances, and that's not good either. So somewhere in between, 0.707 is like where you want to live. Anywhere between like 0.7 and like 1 is probably where you want to be. But you can go down to like 0.6, depending on some applications. If you go down too far, though, you're going to end up with these resonance peaks. You got to watch out for those. Okay, first we generate and plot the input square wave at a few frequencies. The motivation for multiple frequencies will become clear later. The angular frequency of the nth harmonic is defined in terms of the square wave period t. So that's that little function there, angular frequency. So 3 periods to explore. So I'm going to use a period of the square wave being 2 pi, period of square wave being 2 times 2 pi, so 4 pi, and then 6 pi. So those 3 periods, which mean that we have a different input spectrum, right? So the spectrum is shifted down more and more for for a longer period, you're going to have lower frequency, right? So you're going to shift everything down in your spectrum, which is good news if we're trying to get below a cutoff frequency that's fixed, right? So we're expecting that when we go to these longer periods, that we're going to have higher fidelity on our output. So we'll see if that turns out being true. So let's plot the square waves, and that can be done using. I showed off there's a way to plot a square wave, or a way to use the square function that's built into SciPy, and so you can just use their function that's built in. It's pretty nice. And the plot looks like this. So we're going to look at the Fourier series results for this. I use the same time scale on all these. So this one has period of, this is 2 pi right here, right? Period of 2 pi. This one has period, this is 4 pi. And then this one has a period, this one's 6 pi. So putting these 3 signals in, and we're going to see what comes out. Okay, the system will be second order and defined via its magnitude and phase functions derived previously. We choose to have a natural frequency of 5. So that was the same that we chose in the last lecture. I just didn't say that explicitly, I don't think. So this is how to do it in the maths. So if you use the maths, you get this magnitude and phase. These magnitude and phase equations. And notice that they depend on zeta and omega. So I write these functions. I don't know why they come in weird with the fonts, but in any case, defining a function of omega and z, and I'm just essentially writing these in the Python syntax. So the only thing that's weird about Python syntax is exactly the same as MATLAB. It's like familiar to most people, but the only thing that's a little different is that instead of using the caret for square, it uses the double star, double asterisk, which is actually like a C thing. C language uses that. So I don't know. I don't really like it myself, but it's something that they like using. So what we're going to do is we're going to plot the magnitude of phase. We're going to use the magnitude of phase to transform this input Fourier series in a minute. But first we're going to plot the magnitude and phase of the frequency response function for two values of zeta. And that gives us this plot. It's a couple pages. And this plot, besides just being generally sexy, although I did not label this axis as being angular frequency in radians per second, that would have been clutch. But you see that this damping ratio of 0.1 leaves us with this big resonance right here at the natural frequency of 5, right? So this is 10 to the 0 is 1, 2, 3, 4, 5. And if you were to draw that up, we see we have our peak right near the natural frequency. So that's also when the phase starts to shift. So we're going to just say that this natural frequency corresponds to our cutoff. This is like, we don't really want to be there. We don't really even want to be close to there. We want to be like most of our components hopefully happen like over here, right? Because then if you get out here, the phase starts to shift, right? Up here, it doesn't shift that much, and it's pretty linear. I mean, you could actually draw a linear approximation of this pretty easily. It's not that nonlinear. Then it gets really nonlinear. So we don't really want to be out here. We really want to be down here, probably here or below, really. But as we saw before, our input has components that are higher than that, so we're going to get some distortion. All right, so at least for some of the input periods. So that figure is generated by just this code here that we skipped. This stuff is just all like saving it pretty for LaTeX. So like really you can make those figures with this code right here, this code right here, and that, which is not bad. 8 lines, something. And look how pretty. For 8 lines, I mean, that's pretty good. Usually you can't get something that pretty for 8 lines of code. It's a good trade. I like that. So now we must write the Fourier series of the outputs. We have the Fourier series of the input. We solved for it before, right? And we talked about it in the last lecture as well. Remember, all the ANs are 0 and the BNs are 0 when their n is even, and they're 4 over n pi when n is odd. So that's the AN and the BN. I define an AN function of n. I define a BN function of n. I define a CN function of n, which is just the square root of AN squared plus BN squared, right? That's what I define CN to be. Phi n, also just to define as being the arctangent of it's BN over AN, typically, but so what it is in this problem I made what did I use? I used the opposite. Usually A corresponds to the cosine and B corresponds to the sine, but I did like the opposite. So then like our A's and B's are a little bit wonky, but as long as we're consistent, we'll be fine. Yn is just going to be, we talked about all of this in the last lecture. These are all the same definitions from the last lecture. So the magnitude of the frequency response function times C is the new magnitude. The new phase is the original phase plus the phase of the frequency response function. And then we'll do a partial sum. So we'll sum up the first capital N terms, and that'll be our approximation of what the full Fourier series is. We can't sum up an infinite number of terms, so we're going to sum up as many as we can without bogging down the computer. So those are our definitions, our function definitions. And now we turn to the three plots. So one for each input period. We're going to plot the output, so the input signal, the three periods that we chose, remember, were 2 pi, 4 pi, and 6 pi for the input. So we're going to have three plots, one corresponding to each of those. So we expect that our output will be more closely will more closely follow the input for larger t, because fewer significant components, Fourier components, will be greater than the cutoff frequency. In this case, the natural frequency of 5 radians per second. So we really want to get as much of that signal's significant components lower in the frequency spectrum. And we can do that by increasing our period, which makes the frequency smaller, right? So each of those components, you could think of the line spectrum as sort of like squishing down towards the origin when we do that. So that's what we expect. We also expect our output to more closely follow the input when the damping is around 0.707 rather than when it is around 0.1, because the resonance effects should be absent at 0.707. So remember, wide and flat. So I'm going to sum up the first 200 terms because that's a reasonable number and it didn't bog down my computer too bad. And I'm going to do zeta of 0.1 and 0.707. I'm choosing for my period to be T1, which was 2 pi. I'm going to plot the input first. So if we look at the thing coming out, the blue line is the input line. So I didn't ever get to a legend here. So blue is the input. So it's just the square wave. So it looks just like it did in the previous graph. We just plotted all the square waves. So square wave. And so ideally, our output's going to look exactly like the input. I mean, that would be like the best scenario, right? Our system is 0 order, and it just comes out looking exactly like the input. But that's not realistic. Real measurement systems don't do that. So we have instead to plot what we get for our Fourier series. So what I do is this double for loop. I say, okay, I have two values of zeta. I'm going to do a plot. I'm going to plot on that graph two different values. So I pick out zi means the z at that in that loop iteration, and z now is that z now array here. So I'm selecting out one, go through the loop, select out the next one, go through the loop. PS is the partial sum. I'm just initializing it to be an empty array. And then for each time value, I'm going to append a partial sum. So for each time value, I'm going to add up all of the sums for this system. So I gotta sum up each term at each time value. You could do it the other way, but you can't. Well, it doesn't really make sense to do it the other way because you're going to plot versus time. So you can't really sum over time. So you pretty much have to do it this way. For each time step, you can do it this way. You can vectorize it too, so-called vectorizing it, which makes it faster. But I feel like it's better to do things like this in an intro class where you guys are still kind of like a little hazy on the programming. For loops are less structures that we're familiar with. so we can use them, no problem. Having them nested is totally fine. All it does is it goes through each possibility for each other possibility. So for instance, there are 2 z values, and then there are like 200, or t is, I forget how long t was. How long did I make t? Way back here. (201). So 201 values of t. So this outer loop happens twice, right? Because there's only 2 values in z now. This inner loop happens 201 times. It goes through each time step, and it does this sum. And then I plot that partial sum in time and for each z value. And the result is, so the first z, so if I use z of, so the orange corresponds to a zeta equals 0.1. And that was the nailed it graph I sent out. So it looks a little like a square. It wants to be a square wave.
It's
You
like
can tell.
if you put triangles on a square wave, it would look very close to that.
Yeah, if a square wave had fins, it would be like this. So this is, I mean, we didn't, like we could maybe do better than this. This isn't really that great. If I saw this and I knew that I was really measuring a square wave, I would be like, we could do better. We could do better than this. So, not ideal. Then with the green one, we have a zeta of 0.707, and we get this much closer green wave, which is kind of like a square wave. I mean, no dynamic measurement system is going to look exactly like the square wave, because square wave changes instantaneously, but a real dynamic system can't, so it's going to always have some.
It can be infinitely close.
Yeah, so you could, what you could do is you can improve if you could essentially scoot your if you could move your natural frequency like up more and more, you would get better and better. And that's actually essentially the equivalent of what we're going to do. Instead of that, what we're going to do in this example is we're going to say, okay, what if we tried to measure a square wave that, and this legend works for all of them. We've tried to measure a square wave that was just a little slower. Like it was half as frequent. So the period's twice as long, and that's what this one is, right? So you see, you get the same response. I mean, you could think of this as looking just like a response of the system to like a step input. It responds in the same exact way. It shoots over too much, and then it comes back and it has this wave thing. Well, up here, halfway through this, we were like, okay, and you're done, right? And then we moved on to the next part. Here, you have more time to settle down, so it actually settles down close to the square wave value out here. It's bad in this first part, but it does okay out here. And then you can see if we slowed it down even more, then it has the same response again, but it by the end, it's like actually looking pretty good. And then it takes a little while for it to come back each time it changes. Whereas the green is just looking better and better, right? Relatively, if we plotted these so that you plotted the same number of periods, so this was, what, like 2.5 periods or three periods up here. If I plotted 3 periods of each of these, then this would look like I'm getting closer and closer to approximating the square wave. Because this green line is going to, the gap here is going to, as we zoom out, it's going to look closer and closer to it. So you can think of it as you're trading off. You could either speed up your system by increasing the natural frequency or the cutoff frequency of your system. That's one possibility. Or you could slow down the square wave that's coming in. If you have those options. I mean, oftentimes when you're doing a measurement system, you can't slow down the square wave, right? Like, the signal is what it is. Like, you're trying to measure what it is. So,
Make it work faster.
sorry?
Make it work faster so then you...
Right, and that's what we do by moving omega n out, essentially. Like, we can have the same impact of getting better and better if we move omega n out. But you have to design your measurement system so the omega n's further out. So this is like exactly the type of thing that we're going to be doing on your take-home exam project thing, where you're going to say, okay, like I've got this measurement system, or maybe we're going to design it, and I'm going to ask you to do things like make the performance better, like choose parameters so the performance gets better, show that the performance got better, that type of thing, which is very practical stuff. And I do think I like that because this theory that we've been doing is super practical, but I do think that it's hard to see how it's super practical until you get it applied to stuff. So I'm looking forward to having you guys work on those problems, and I think you guys will have fun with it. So, any questions? So the homework that I gave you for this week, is essentially just like more practice on chapter 3 stuff. We can have a quiz over it, or we don't have to. I'm open to either option. If you guys don't want to have a quiz, we don't have to have a quiz.
I gotta wake up at 5:30 tomorrow.
Yeah.
Work 9 hours.
So,
I'm not looking forward to it.
yeah, I mean,
Wake up at noon tomorrow and not work.
I mean, it could have, it could maybe have a positive effect on grade. I mean, that's the thing. Like, it could go either way. If you have the homework done, though, I wouldn't want to like be like, oh yeah, like so like you don't get to pick up any quiz points. So if you do, if anybody feels strongly like, yeah, I think we should have a quiz, then we can. Otherwise, I feel like it's been a pretty bad midterm week for a lot of folks. So I feel like maybe we could just have a quiz week off. Just
What classes had midterms, just out of curiosity?
Thermodynamics, manufacturing.
Mechatronics,
My
material
class,
science.
Vector cal.
So I'm in none of those classes.
So you're itching for some work.
I did at least half of the homework. I vote that we do not have the quiz.
I think we're all good
Because
with no
then